Welcome back to Retro Depot. This is the second video of digital logic design, and today we're going to be looking at I/O decoding. And in the last video we took a look at a memory mapper, a pretty complex design, but one that's simple enough to understand once you get an idea for what the intended goal is. Today we're going to be looking at something much simpler, but you know, a lot of people just don't understand decoding that much, and you know, it is what it is. So we have a couple things that we are going to be doing in this circuit, and they are all very similar. So essentially we need a couple of different I/O devices hooked up, and the reason for that being is because this is actually a larger project that I'm doing. So we're going to need a total of let me see here, about 9 I/O signals, I/O chip selects. Now, not all of these will be used in the final design, but it gives us a little bit of playroom to be able to mess around with this. So the first thing that we're going to do is construct the basic circuit of how we're going to decode this, and we're going to use OR gates. So if we get an OR gate here, and we construct it as such. Well, let me actually drop this down just a bit. We are going to need a total of 6 OR gates per chip select signal. For one of them, we're actually going to need an additional one. Actually, there's a couple of them that will need an additional one. But this is not too hard to understand. And the reason for this being is because if any of these signals are high, then that means the output is going to be high. And for just about every chip select I've ever seen, they're just about always active low. Now, by constructing it this way, we have enough pins for, let me get these out here, a I/O request signal. We have A7, A6, A5, A4, A3, and A2, and that's going to give us 2 bits for the address lines to be able to route those to essentially any chips, any I/O chip that we're going to use. So for example, the 8255 PIO, you know, it needs I think 2 address pins. I think the for example, the 9918 Texas Instruments VDP, it requires 1 address pin, but you never know how many you're going to have, so it's good to give yourself a couple extra addresses, because even though we're going to be labeling these as certain things, that doesn't mean that we have to ultimately use them as such in the future. So I'm going to do a little bit of housekeeping in this circuit real quick, and we will be back. Okay, we are back. And now we have our circuit put together, and we can simulate this. So for example, if bit 7 and I/O request are high, we obviously get a high on the output. If I/O request goes low, it's still high, but once we drop A7, at that point we start getting that low output, which is what we need for essentially pretty much most things. There may be some chip select signals out there that require an active high, but yeah, you know, if you need it, you can always put a NOT gate on it use a 74HC04 or something similar, maybe a 74HC14, a good Schmidt trigger. So lots of options there for you to convert that signal if you need to. But this is the basis for everything that we're going to be doing. And we've got a total of, I think, 9 different chip selects we need here. So the first thing that we need is we need a chip select for a DART. Now, the DART on the G80 computer that I designed is at address 00 through 03. So that is pretty much what this circuit is going to decode for. The next one that we're going to need is going to be a UART, another UART. And the reason for that being is because I'm actually going to design a UART in Digital Logic. So we need an address location to stick it at, but it's going to be kind of a testing phase for the first couple versions of this board. So that said, we want to go ahead and have the DART there as well, so that we have a reliable serial port if we need it. So we're going to put that at address 08 hex. Now the next one that we're going to be looking at is another video port. This is for an 80 column video controller, and it's going to be at port 10H. We are also going to have a sound chip at port 1C. And then another video controller, either the TMS 9918 or possibly the 9958, is going to be at memory locations 14 and 15. I'm going to have a game port to read a Sega Genesis controller, and that's going to be at locations 30 and 31. And we also need to make sure that we give ourselves a output for the PIO. So we're going to use ports 80 through 83 hex for that, just like on the G80 computer. And a lot of the reasons why I'm choosing these same address ports is for backwards compatibility of code. Now we're also going to have we're going to implement some type of FAT file system. So I know I'm going to need a chip select here, so I'm going to choose my base address for that at address C0, and that's going to give us I think that's going to give us a total of 9 total. I believe so. I believe it's 9. Also a keyboard. We're going to have a actual IO mapped keyboard, so we're going to stick that at address location E0. So that's 9 altogether. And for each one of those, we're going to use this same basic circuit. So what we're going to do is we're going to copy and paste this. So we're going to press Control C, Control V, and we're just going to drop this right here. Now we already have this labeled. Well, we need to go ahead and label it as DART chip select. Now the next address that we need to prepare for is going to be the 80 column video, and again it's going to be address 10H. So that means that we need to modify this circuit a little bit. Now if you were using a if you were using a actual IC, some just discrete logic, let's say that this is IO request bit 7, 6, 5, and 4. This bit is going to need to be high, which means that in this circuit we're going to have to convert it to a low when it's high. So typically what you would do is you would NOT this. And the great thing about Digital Logic is we don't have to think that way anymore. We can let the software do this for us, so that we can essentially reuse parts. So we can delete this, and we can right click on the OR gate, and we have this little section here where it says inverted inputs. Okay, now if we select that, we can go ahead and select this for a NOT gate. Okay, and that's fantastic, because now if we look, it's going to take a high on this to drive the output low. But we can simplify this circuit even further, okay? And the way that we are going to do that, let me get rid of this, is by dropping a single NOT gate out here, and we actually can specify the number of inputs. So we know that with this particular scheme we need a total of 7 inputs, okay? So if we go here, we can select up to 5 through the drop down menu, but we can manually put 7 in, okay? So now we have 7 inputs, and we know that the 5th input we need to be a NOT gate, so we can actually set that as a NOT. So now we have a much more simplified circuit. Now it's a little bit more whenever it comes to mapping all these wires out, so I'm going to take a minute and do some more house cleaning and get that set up so that we have all of our chip selects done. That way we're not wasting time. You guys have something more to do, and I'm just here to describe the circuit for you. That way you have a good understanding, and that you understand how this ASIC, so to speak, is going to work once it's done, in the event that you decide to reuse some of my work. Okay, so give me just a minute. I'm going to clean all this up. I'm going to get all the chip selects out there, and we will be back in just a moment. Okay, we are back, and what we have here is basically our I/O decoding. Now you can see there's a couple of things that have been left unconnected, and I'm going to go over those here in a few minutes, but first we're going to talk about the function of this. So essentially we've used the same style for generating each one of our chip select signals. In reality, if you were doing this on a breadboard or prototyping board, or even making a PCB, it would probably be easier to use like a 3D8 decoder or something along those lines in order to generate chip select signals. But since we are working in a digital environment where we can design this from the ground up, we can essentially use individual gates in order to minimize how much logic we're actually going to use, especially when we're talking about CPLDs. I think I mentioned in the last video the CPLD I plan on using for this is the Max 7000 series. It's the 128 macro cell version. It's the EPM 7128. So that version has about 2,500 usable gates, and each macro cell of the 128 has exactly 1 flip-flop. So it's important to try to conserve so we can cram as much into this thing as possible. And of course we're going to talk about that here a little bit, but essentially that's what we're doing here. We're using OR gates because OR gates and NOT gates, they don't take up a lot of logic internally. If you start getting into like 3 to 8 decoders, it can ultimately end up getting fairly expensive logic wise, but we've decided to use this method. Now the great thing about that is because in this we can use essentially the same circuit. We just change the input, whether it needs to be high or low, and as you can see I've done that with several of these. So we're going to test this out, and the first thing we get is an error. It says no output connected to a wire, and it showed me this one, so I tend to think it's probably that one. Let's try that one more time. Oh, no, CSR. So let's just get rid of these for just a moment. Now we can test it. Okay. So as we fire it up, we see Dart is automatically asserted, and that's because A7 through A2 is low, and IO request as well as read and write are both low. Of course, read and write are not currently used, but we can get the current idea as far as what we need to do. So we know that if we just cycle IO request on and off, we're going to get a low on the Dart. Now if we go to the UART and we set it to address 08, we're also going to get a low. Let's just go through these one at a time. The next one is going to be 10. So we see that on the video 80 chip select we're getting an out. I don't have the rest of the logic hooked up for the VDP, the TMS controller, video controller that is, so we're going to skip that one for now. If we go to our sound chip, that's going to be 1C, so we'll set that to 1C, and as you can see we get a low out, and we can go on down the line. You know, each one of these is going to have a very, very similar pattern. It just allows us to get everything down on paper, I guess you could say. Let's try C0. And as you can see, our gain port works. The next one would be the PIO, and that one works as well. Our FAT controller is going to be at C0, and of course that works as well. And lastly, a keyboard decoder, and we need a chip select for this because we're going to be reading it from a octal buffer. So we actually have that mapped to E0. So if we flip that bit, there we go. So we know it all works. The next thing that we need to do is we need to construct our chip selects for the VDP. Now, we've got our basic decoder here, but the VDP has two signals. One is CSR and one is CSW, and it stands for chip select read and chip select write. It's one of those chips that doesn't have a chip select and a read, a write, or just a read-write signal, like on the 6800 series of chips. So what we need to do is we need to add in two more pins here, and I'm going to stagger these as best as possible, that way I can try to keep the schematic neat. And along with this, we also need a couple of OR gates. Now, the thing to remember here is that because this is a read and write, we need to OR these with read and write. So we want to make sure that we have our chip select signal hooked up, and we're going to bring in the write signal first, and secondly we're going to pull in the read. There we go. Let's call this CS write. Let's take that back. That's actually the read one. I believe it's read. We could always rename them if we need to. But now that we have that, and we go ahead and try to simulate this, if we set our address to port 14 or 15, yeah. So let's drop write first. If we drop IO request along with it, we get our CS write pin, and if we flip these bits, we get our CS write pin. So our chip select write. So that works. Now the next thing that we need to talk about is the keyboard. Now, as I mentioned before, this will have a keyboard decoder in it, so that we don't have to worry about trying to generate that signal externally. We can stick it inside of the CPLD as well. The idea is with a CPLD we can put a whole lot of stuff inside of it, and so long as we are careful in how we build it, we should be able to fit everything that we need in there for the most part. And that's part of the reason for the UART pin, in addition to the SIO or the DART chip select, is we are going to incorporate a serial port internal to the CPLD as well, and it's going to be very basic, but we'll cover that in a later video. So for now, we've got our logic laid out. The next thing that we need to do is to do our keyboard decoding. So I'm going to pause the video and I'm going to get that built. Okay, we're back, and with this decoder here, it's pretty easy to understand. You just have to take a little bit of time to figure it out. Now, Digital calls this a splitter, I believe. Component that can output the input value to one of the outputs. The other outputs are set to default value. Let's see what they actually call it here. Yeah, it's called a splitter or merge. Well, no. Yeah, it's just a multiplexer. Okay. So this is a demultiplexer is what it is, or decoder, essentially the same thing. Now on this, it's constructed pretty simply. We're using A0, A1, and A2. We're running it through this splitter to actually merge it into one signal to stuff into the demultiplexer, which is a 3 to 8 decoder essentially. And then we have the enable just tied to VCC, because we don't really need to trigger this any particular way. As a matter of fact, we prefer that these signals always either be going high or low and not have to worry about chip selects. And the reason for that being is because for every single component that you have that's in the line of I guess you could say in the daisy chain of items that you have to have active in order to either read or write your signal, timing becomes an issue. So we want these to go high or low as quickly as possible. That way when we read, or read, because we're not going to be writing, but when we read from it, we want that value to be present as quickly as possible. We don't want to have to wait. And that's essentially what we've done here. So we're actually already booted up in simulation now. As you can see, column 0 is lit up, and the reason for that is because all 3 of those pins are low. If we raise 1, we get column 1. Second one, we get 2, we get 3, 4, and so on up the line. So with that, that actually completes our decoder. And we've got, like I said, quite a bit of chip selects here. That's more I/O than most do-it-yourself computers actually have, or at least a lot of them anyways. There's some of them that probably have more, but you know what? They're not on a CPLD for the most part. So we've got this all internal. This isn't going to use up a lot of logic. This is only going to use up a very small amount of gates. You're probably looking at a couple macro cells, because OR gates, they're cheap whenever it comes to CPLDs. So that's it for the decoder today. Kind of a short video, kind of long, probably something that most people don't really need to watch as far as how to construct these, but it's nice to see how to do it in a program such as Digital, which can again export to VHDL, which is very important because, like I said, we are going to be stuffing this into a CPLD. The CPLD is going to effectively act as an ASIC, if you will. So it's nice to have that feature so that we can build very small compact boards that have a lot of stuff going on. PCBs aren't cheap. They are, but whenever you start getting into bigger PCBs, they are not cheap. And the particular PCB that this design in general, I've already built this computer in a traditional method, with the exception of using a couple of PLDs to simplify some of my decoding. But I've got a lot of other logic on the board, and I'm trying to combine all of that into something that's a little bit smaller. Currently that board is about 300 millimeters by 100 millimeters, and I forget what I paid, but it was close to about $60 to $70 shipped for a batch of boards. And if I could get that size down to something more in the area of, let's say, 200 by 100, that would create for a much smaller board that is a little bit more economical for not only my own purposes, but also in case anybody decides to build this in the future. So that's part of the reason why we use CPLDs, is so that we can shrink our designs and we can add a whole lot onto one chip. And this isn't a new concept. This is something that companies have been doing for a very long time. You know, at first it was called LSI, large scale integration, and then VLSI, you know, very large scale integration. And then you started actually seeing, true ASIC type designs. And, you know, that's very similar to what a CPLD is. We are taking technology of the day and we are squeezing it onto one chip so that we can have a whole lot of features in a very cost-effective manner of production. And for the hobbyist, you know, that's one of the keys. I don't know about many of you, but I spend a ton of money on parts and boards and everything else. And if I can compress that into something that's cheaper for me to build, it actually helps out quite a bit on the pocketbook. So that's part of the reason why we use things like PLDs, and that's part of the reason why we would use things like CPLDs as well as FPGAs. So, and of course, this here, it's applicable to either one. Now, this program also reportedly has a way of exporting to code that's compilable under CUPL. You're going to have to get with the guy that is designing this software, though, because I'm going to be honest with you, this is some of the least user-friendly software I've ever used whenever it comes to figuring out some of the finer features. The actual circuit construction as well as the exportation is pretty seamless, but the other features with the code, not so much. So the next video we're going to take a look at is going to be the UART. We're going to construct a UART so that we can get this design put together. And then I think that the final video will be putting everything into one package that we can then turn around and put into a CPLD in Quartus and compile it and see how it goes. See if we've got enough space. We may have to make a couple changes, but I anticipate that we are going to have more than enough room. So thanks for watching. If you've got any questions, be sure and leave them below. Other than that, visit the website, www.retrodepot.net. There will be a link in the description to a short write-up on this, as well as to the code that I will be hosting on my website. Once the entire series here is done, it's going to be about a 4-video series. I'm going to post the zip file with the VHDL code for the entire package, as well as the POF file for the CPLD, or the EPM 7128. That way you can download it and essentially use my design if you choose to. Alright, so again, thanks for watching. Check out the website, and as always, subscribe if you're not a subscriber, and hit like if you like the video. And I'm going to try to do some more videos with this software. It's really fun to use. It's just a little bit complex, and it's not as bad as Quartus, but it is still kind of hard to use. So, but anyhow, we'll see you next week.